subject for the 6th video is energy dimensions, and we're going to really jump from talking about protons and neutrons and other relatively large bodies to the very, very smallest bodies that could possibly exist. And we won't spend time on the bodies that make up protons. That's the job we'll leave to the Large Hadron Collider and their scientists. We're going to go right down to, I suppose you could say it's related to what's called the Higgs boson, but I just think of it as the most minute of particles of matter that can possibly exist. So small that you can consider it as having no size and shape. And so I'm going to then describe how these particles relate to one another by means of the energy relationships, and this will lead us to discuss mass further than we did in the previous video. So let's talk about the very, very smallest particles that can possibly exist. So small that I'm going to draw them as circles and say that there's one in here and there's one in there, but they're so small we couldn't draw it. But there's a fundamental particle of matter. I'm not going to talk about mass. I may accidentally say mass, but you remember we said last time that mass and matter are not the same thing. Mass is a property that we attribute to matter, but they're not the same numbers when you start talking about very high velocities. So I'm going to be referring to matter, even if I use the word mass. So matter is substance, that which actually fulfills a very, very simple purpose. It is simply the ends of a separation in a dimension. So you can say that there's space between these two units of matter. And that space is there because the units of matter mark the ends. And that's about all they do, is to be the nodes or points where separations end and where they meet one another. So that, for example, these two units of matter can be separated by space. And space is only one kind of separation. We've already seen time in Einstein's special theory, that time separation, the difference in time between two bodies, is what causes the increase in mass. Because in order to move to a different location in time at the same time as it moves in space, it has to fight the river of time, which is traveling at the speed of light. So that's why you get this increase in mass, because there's a much greater resistance to that kind of acceleration against time. Anyway, space is the visible dimension. Time is not visible. Of course, we can't see differences in time. We see differences in space actually for a reason that I'll get into some other time, but it's because space has a very special conservation law protecting it, and that is that space can never be zero. Bodies must always be separate. Even if they're touching, like touching this board, there's always one quantum of space between my hand and the board. You can't see that, of course, but it's rather important because it means that two bodies of matter or mass cannot occupy the same space. That's how space is conserved. But there's a separation we saw in time. I'm drawing, of course, time was going this way before and space was going this way. It doesn't matter which way you orientate them, because direction means really nothing. It's more the separation that's important. So we'll say that's time. So if you have two bodies separated, I say bodies, these are units, but bodies are really just collections of units. So a body acts as its units acts. The Earth is made up of units of matter, so small we can't see them. But that's the body of the Earth acts as all these other units act, and it's the sum effect of, is what we call the effect of the body of the Earth. So that, since these two are separated by space and by time, then this other unit of matter here is not here, it's here. And that's now the separation. And you remember, if we turn this around the other way, this is the kind of separation we saw before that I called S, T, meaning the effective speed moving through space at a high velocity. So this is actually the separation. Well, this is a right angle. And we used the theorem of Pythagoras in order to relate these three sides. This squared equals this squared plus this squared. There are different kinds of separation. That's why you have to add the squares. You can't just add the numbers. 2 plus 2 does not equal 4 in a situation like this. But 3 plus 4 equals 5. In other words, 3 squared plus 4 squared equals 5 squared. Anyway, now these are 2 dimensions. Now we can actually add more dimensions, but to do that I'm going to deal with something that's a little easier for us to understand. I'm going to deal simply with space, because we understand the 3 dimensions of space better than I think we understand the dimensions of space and time. So let's consider 2 dimensions of space. Here's a body. Let's say this is a child on a beach flying a kite. And there's the string between the child and the kite. And let's say that this kite is so many, certain distance north, and a certain distance, shall we say, that would be west, wouldn't it? So it's a certain distance west. So the kite is northwest to the child. And that's 2 dimensions of space. This is the view you would see looking down on the child as the child flies the kite. But the kite is also in the air, which is in this dimension, coming out. Well, I can't draw that, but what I can do is I can take this distance and I can then say, okay, the kite really is in the air up here, looking down on it, it's up here. Now the kite is this far from the child, and I can take this triangle here and push it over so that that is again a right angle. So this, you see, is the height pushed around, hinged on this line here. So that now is the kite. This is the kite now. And this is the height. That's the north, and this is the altitude or the height of the kite. So now this is the actual distance of the, between the child and the kite. In other words, this is the string that's holding the kite. And as you see, you can, because this is another triangle, then this squared plus this squared equals this squared, and this squared is this squared plus this squared. So that the length of the string is equal to the height of the kite squared plus the separation north squared plus the separation west squared. So this is the theorem of Pythagoras in 3-dimensional triangles. And from this we can then see how you can add even more dimensions, because if you added another dimension, which we're going to do probably now, it will seem like the next video, but I may try to fit it into this one. That if you add another dimension, you can add it on here with a right angle here. And any triangle that you add here to this line is perpendicular to this line, which is the sum of those 2 perpendicular to one another dimensions, which is, and this one here is the sum of these 2. So you can keep adding dimensions, and the 3 dimensions of space is a limitation that we experience because we just can't think in terms of more than 3 dimensions. But you could have a lot of dimensions, and you add them all up simply by adding more squares. And so you could have 5, 6, 7, 9 dimensions, many consider there are altogether, that you have to consider when you're talking about subjects such as general relativity. But you add them on simply by adding another right angle, and you can unfold a multi-dimensional body in this manner. Stephen Hawking tried this in his first book, The Brief History of Time. But he was trying to unfold a rectangular body that was 3 dimensions, unfolding that to 4 dimensions. Now, I find that difficult to follow. With a triangle, it's much easier. you can unfold it easier. So this, as we see here, is a three-dimensional triangle. This is the longest side. This is the another intermediate side, and there's also a side between this point and this point that we would see if we were to bring this back up again. You would see there would be a separation there. That is the sum of the vector sum of these two separations. So it's a little complicated, but if you flatten it all out, you can keep adding to the longer side. And that longer side is very important to us because, as we're going to see, I think it'll be in the next video, that the energy between two bodies can be represented by the total, the longest side of a multi-dimensional, at least 4 dimensions, or 5 perhaps, or even 9. That is the longest side, which is the sum of all the other sides in a multi-dimensional body, gives you the total energy. And that is what explains gravity, because the longer side, like the string on the kite, doesn't change its length. A kite can move all over the place, but that string can stay the same length and the kite can move around. And so gravity allows the sun and the moon to orbit the Earth, let's get it right, the moon to orbit the Earth, and the Earth to orbit the sun, and the moon to orbit the sun. All of these can move, but their total energy, which is the sum of all the separations in all dimensions, is constant. And that is an explanation of gravity that we'll go into on another occasion. So thank you. This is the 6th video, and we'll end that now. Thank you for watching.